Without further ado, I'd like to welcome Rachel Greenfeld from UCLA, who's going to speak to us about translational tilings. So welcome, Rachel.
Thank you very much for the invitation. And as stated, we are going to talk about the structure of translational tilings and its relation with decidability of tiling questions. So let's start with introducing the notion of translational tiling, and we'll do it first in the Euclidean space. So here we consider a bounded measurable set omega in Rd, and we ask whether there exists a set T in Rd such that the family of translations of omega along T constitute a partition of the space up to measure 0. In other words, almost every point in Rd gets to be covered by exactly one of these translated copies. If such a set T exists, then we say that omega is a tile of Rd, as omega translated by T form a tiling. And this sum here refers to Minkowski sum. It means translations. For example, here are 3 translational tilings of the plane. In each of these cases, the tiling set is a lattice, namely a 2-dimensional discrete subgroup of the plane. And the tiling is unique up to translation. So in this sense, these structures are very rigid. And here is another example. This is a real-life example from our backyard. As a lockdown activity, we tiled our backyard with grass. And this example is already less structured. In particular, the tiling set is not a lattice, but we can still see a 1-dimensional rigidity along each horizontal line, along the rows. Now, let's consider the most classical tile, perhaps, of the Euclidean space of Rd, the d-dimensional unit cube, which I denoted here by Qd. And perhaps the most naive cube tiling would be along the integer lattice. This yields a face-to-face tiling, namely each face of each copy is entirely shared with the face of another copy. Now in the 1-dimensional case, this is the only possible tiling by Q1. So in this case, the structure is very rigid. For Q2, however, in the plane, we already have some flexibility. We can either shift the rows horizontally or we can shift the columns vertically, as the central figure here illustrates. But still, each copy will share at least one common facet with another copy. In 3D, as the example in the right shows, there are tilings by Q3 with copies that do not share any common facet with any other copy. But still, we can ask, could it be that all the copies are such? Does there exist a tiling by QD which does not contain 2 copies sharing common facet? By the way, by a facet, I mean a d-1-dimensional face. So in 1930, Keller conjectured that this is impossible in all dimensions. This is the celebrated Kellers conjecture, which suggests that, that any tiling by QD must contain 2 cubes sharing a common facet. To support his conjecture, Keller proved that the conjecture holds in dimensions up to 4, and 10 years later, Piron showed that the conjecture holds in dimensions up to 6. But perhaps more importantly, Piron proves that the question of cube tilings can be reduced two tilings by a bounded subset of a certain lattice. Or more precisely, he shows that if there is a d-dimensional counterexample to the conjecture, then there must also be a counterexample which is 2ZD periodic, namely it is invariant under translations by point in the lattice 2ZD, and it is contained in this certain lattice. So Perron discretized the question and bound it. And so this implies that there are only finitely many configurations that we need to check in order to answer the question. And this shows that for each D, the question is decidable in RD. Namely, there is an algorithm which provides an answer in finitely many trials. So now it's kind of just a matter of time. So this reduction of Perron enabled a reformulation of the question to a question of on certain property of a certain type of graphs, finite graphs known as Kellers graph. This was done by Corradi and Jabo in 1990. And using the Wang counterexample were explicitly constructed first by Lagarius and Shor in 10 dimensions and higher. This was done in 92 and later by McKee in 2002 in dimensions 8 and higher. Now notice that the fact that counterexample to the conjecture exists in higher dimension demonstrate that the higher the dimension is, the worse the structure of the tiling is. So we have less and less rigidity and more degrees of freedom and flexibility. So now we know that Keller's conjecture fails in dimensions 8 and higher, and it is true in dimensions up to 6. And the only remaining case, the 7-dimensional case, was proved to the affirmative very recently by Brakenzik, Heule, and McKee. And in fact, their proof is computer assisted. So we see that this reduction of Perron, which discretized and bound the question by periodicity, enabled the resolution of Keller's conjecture. There is a lot more to be said about the study of Keller's conjecture, but here I didn't get into too much detail because my main purpose in introducing this study is to demonstrate the importance of the study of the periodicity of tilings and in particular of tilings in lattices. So imbued with this motivation, let's focus on tilings in ZD. So here, a tile is a finite subset F of ZD, such that the whole space ZD can be partitioned into translated copies of F. And notice that we can reformulate the tiling condition as a convolution equation. And now the question is about the existence of a set A in ZD, such that the convolution of the indicator of F1 sub F with the indicator of A would give us the constant function 1 on ZD. In case such a set A exists, then we would say that F is a tile of ZD, where the translations of F along A form a tiling. So again, this is a Minkowski sum, and it means F translated by points in A. So this is the definition that we are going to work with. So let's try to digest it with some examples. And the simplest example would be any set of cardinality 1. Any such set is a tile of ZD, as if we translate it along the integer lattice, we cover any point of ZD exactly once. So the tiling condition is satisfied, and we have a tile. In fact, this is the only possible tiling by a set of order 1. So in this sense, the tiling is rigid. So okay, this was quite simple. Let's then consider an example of cardinality 2. For instance, this one-dimensional subset of the integers, the points 0 and 2. So this is indeed a tile of C, because if we translate it along this set A, which is a union of two progressions, we cover any point in ZD exactly once. We can illustrate this fact geometrically, and we can also check it algebraically just by computing this Minkowski sum. And notice that in this case, the tiling set is no longer a lattice. Here by a lattice, I mean a subgroup of finite index. But still, it is a union of two cosets of the lattice for Z. And therefore, it is periodic. Now, I already mentioned this notion of periodicity, but let me now formally define it. So for a set S and a subgroup lambda, we say that S is lambda periodic if S is preserved under translations by any point in lambda. In the special case where lambda is a lattice, it has a finite index, then we can simply say that S is periodic. For example, the tiling set A from the previous slide is periodic with respect to the lattice for Z. So now we are familiar with the notion of translational tilings, and we know what is periodicity. And from the example of the study of Kellers' conjecture and the way by which it was resolved, the interest in studying periodicity of tilings is clear. The periodic tiling conjecture, which is perhaps the most well-known conjecture in the area, suggests that if F is a translational tile of CD, then it must admit at least one tiling which is periodic. This conjecture was explicitly formulated by Bhattacharyas and Wang in '96, and it was also posed implicitly earlier by Greenbaum and Shepard in '87. Let me emphasize that we have already observed that there are translational tilings which are not periodic, as we can see here. But the conjecture suggests only the existence of at least one periodic tiling for a given tile F. The study of this conjecture involves methods from various fields, and I want to mention here some of them. So first, as a geometric question, it can naively be attacked by geometric tools. And in addition, as we have seen, tiling questions can be interpreted as graph theoretic questions or coloring questions. And therefore, combinatorial techniques are relevant here too. Also, Fourier analytic techniques are applicable because notice that this tiling convolution condition kind of begs to be subjected to the Fourier transform, which will give us this product equation that we have here in the right. And these two are equivalent by the uniqueness of the Fourier transform. And so we can use Fourier analysis to study the distribution 1 sub a hat in the zero set of the trigonometric polynomial 1 sub f hat. Also, ergodic theoretic tools are available in the study of structural tilings in ZD, because tiling sets A of ZD by F can be viewed as an ergodic point process. And so spectral analysis can also be applied to the study of the spectral measure of this process A. Moreover, elementary number theoretic arguments such as the Frobenius endomorphism, we'll see it, and some probabilistic methods have been found useful to the study of the periodic tiling conjecture. So as we already observed, one example of the importance of the study of the periodic tiling conjecture is its connection to decidability. And let me elaborate a bit more on this. So given some finite subset f of CD, could we decide whether f is a tile or not? Or in other words, is there an algorithm which provides an answer in finite time? A well-known argument that was first presented by Wang shows that a proof of the periodic tiling conjecture would imply the decidability of this tiling question. And let me make the argument here. So clearly it would suffice to check whether f can tile all the possible finite regions, starting with the smaller and working up. If f is not a tile, then the obstacle must show up at some finite step. For instance, if we consider this one-dimensional set, this the points 0, 1, and 3, the subset of the integers, we see that there is no way to cover the point 2 without overlapping. In this case, the obstacle will show up in a very early stage, but in general, if f is not a tile, we will see it at some finite step. Now, otherwise, if f does tile, then a periodic tiling exists. And so one of these finite regions will show us this periodicity, and the tiling then can be extended to the whole space. For example, if we consider again this tile, the one-dimensional tile 0, 2 of the integers. So what we do, we tile this interval, and it's clear that from here on, we can just continue periodically. Therefore, if the periodic tiling conjecture is true, then this tiling question is decidable. So let's start with studying the one-dimensional case of this question. Given a finite subset of integers, can we decide whether it is a tile of Z? So in this case, it is not difficult to show that the answer is positive, as the periodic tiling conjecture is true in this case. And in fact, the one-dimensional case is so rigid that in this case, any tiling must be periodic. And this can be proved by a simple pigeonholing argument that I would like to show you. So first, notice that any window of the tiling set, this is the window of width equal to the diameter of f, would determine the whole tiling. But there are at most 2 to the diameter of f different windows, and therefore there must exist 2 similar windows of distance at most 2 to the diameter of f from each other. And so we obtain that A is periodic with a bound on the period, which is exponential in the diameter of f. So this proves the periodic tiling conjecture in 1D, actually a stronger statement in 1D. And I want to remark here that except for this kind of trivial bound on the periods, this naive proof does not provide any information on the periods. And in particular, it is a priori possible for 2 tiling sets of the same tile to have different periods. And I emphasize this because I will come back to this later. So this is the one-dimensional case, and it was not too difficult. So let's move up to ask the question in 2D. Given a finite subset of a 2D lattice, could we decide whether it's a tile? Or it is enough to show that the periodic tiling conjecture holds in 2D? But before I try to answer these questions, let me illustrate the fact that these questions are already non-trivial at all, as opposed to the one-dimensional case. For instance, if we consider tilings by more than one tile, then aperiodic tilings exist, and the question was found to be non-decidable. So here is an example of an aperiodic tiling of Z2 by 16 Wang tiles and 6 colors. So, okay, we are convinced that in 2D, these questions are non-trivial. But if we restrict ourselves to only translational tiling by one tile, does the question become decidable then? So the answer is positive, as was proved quite recently by Bhattacharyas, who showed that a periodic tiling conjecture is true in Z2, namely any tile F of Z2 admits a periodic tiling. His proof is quite involved, and he uses techniques from various fields, but let me here just sketch the main step of his proof. So first, Bhattacharyas, he introduces a weaker notion of periodicity, which we will refer to as weak periodicity of sets A in Z2. So set A is said to be weakly periodic if it can be written as a disjoint union of one periodic sets. And by using a combinatorial argument, Bhattacharyas shows that from a weakly periodic tiling, one can construct a periodic tiling. And therefore, it is enough to show that any tile F of Z2 admits a weakly periodic tiling. Now, before I proceed in the proof of Bhattacharyas, let me illustrate this new notion of weak periodicity with an example. So consider this tile 0, 2 squared in Z2. So this is indeed a tile, and it admits this periodic tiling, as we see here. But if we, for instance, just shift one column and one row of this A, we obtain a tiling which is no longer periodic or even one periodic, but it is still weakly periodic. So we see that this tile admits strictly weakly periodic tilings. So back to the proof of Bhattacharyas of the 2D periodic tiling conjecture. Given a tile F by this reduction, the current goal is to show just the existence of a weakly periodic tiling. And the first ingredient is a decomposition theorem, which holds in all dimensions, saying that if A is a tiling set, then the indicator of A, 1 sub A, is almost surely equal to a finite sum of one periodic functions, this phi 1 to phi m, and a periodic function phi naught. The proof of the theorem is based on a combination of dilation lemma, which I'll introduce later in this talk, Fourier analysis and spectral analysis techniques, and also a very heavy use of the ergodic theorem. Now notice that if these functions, in the 2D case, if these functions were indicator functions, then the goal was established. We would have had the weak periodicity that we wanted. Now, equipped with his structural theorem, Bhattacharyas studied the 2D case. And he shows that in this case, there is a lattice lambda, such that on any coset of lambda, each of the function phi j mod 1 is almost surely a polynomial, to which he was able to apply the Weil equidistribution theorem to show that on each coset, each of these functions is either almost surely periodic or almost surely equidistributed. Next, by using the first moment method, he shows that the equidistribution scenarios of phi j mod 1 in the given tiling A can be modified to be periodic in a way which preserves the tiling. So after applying a sequence, a finite sequence of modifications to the original tiling A, we would finally obtain a tiling A prime, which can a priori be different from A, which is almost surely weakly periodic. And so the conjecture is established in the 2D case, and hence the tiling question in Z2 is decidable. And what about the 3D case? What does the periodic tiling conjecture hold in higher dimensions? So this question is still open. So with Terry, we then started to study the rigidity of translational tilings in ZD, aiming to understand the higher dimensional case of the periodic tiling conjecture. And our starting point was this structural theorem of Bhattacharyas. So observe that his theorem gives only an almost sure information and not an actual information. Also, it doesn't provide any explicit information on either the function in the decomposition, the phis, or their number, this m, or their periods. And all this information can a priori depend on the chosen tiling set A. So by introducing a completely new approach, we simplified the previous proof and we obtained an improved structural theorem, which again holds in all dimensions as the previous one, but more than that, it holds not only for usual tilings, but under a weaker assumption that this convolution is only assumed to be periodic, not necessarily the constant function 1. We refer to such functions as periodic level functions. Our decomposition is more precise comparing with the previous one, because here the periodic element phi node was what was phi node in the previous notation is given explicitly. It is equal to the periodic level function that we tell. The number m of the one periodic function in the decomposition is given as well as the periods of these functions. And all this information is independent of the chosen tiling set A, and is given only in terms of f and the periodic level function that we tell. This provides a more concrete information on the structure of tilings in ZD. Also, it's nice because it reveals the naturally expected connection between the structure of the tile F and the structure of its tiling sets A. Before we discuss some of the applications of this structural theorem, I'd like to sketch the main steps of our proof. So first, we reproved Bhattacharyas dilation lemma, and most importantly, we generalized it to any tiling of a periodic level function. This lemma states roughly that if A in ZD is a tiling of some periodic level function by a finite subset f of ZD, then there exists a number Q depending only on the cardinality of f and the periodic level function, such that when we dilate the tile f by any number which is equal to 1 mod q, the tiling is preserved. And this is proved by using the Frobenius endomorphism and basic commutative algebra. So before I use this dilation lemma, let me illustrate it with an example. So for instance, consider this tiling of this 4Z2 periodic set by this tile 0, 1 squared. So when we translate this tile by this set, 4Z2, we can just write it explicitly and see that any point of this 4Z2 periodic set is covered exactly once, and we have a tiling of a periodic set. So the indicator, in this case, the indicator function of this set will be our periodic level function. It has only 2 levels. Now observe that when we dilate this tile by 5, the tiling is preserved. And this is due to the fact that 5 is equal to 1 mod 4. Now let's return to our proof of the structural theorem. So if we rearrange the conclusion of the dilation lemma, assuming that f contains the origin, we can always assume that by just shifting the whole configuration, we obtain this equation. This equation holds for any natural number n. And notice that all these dilation factors are indeed equal to 1 mod q. And if we consider the sequence of these dilation factors along n, we have an arithmetic progression with spacing q. And now if we're just focus on each of these elements and we take the averages along this arithmetic progression with spacing q, we can define these functions phi f's, which have exactly the properties that we wanted. Now we have these 2 equations, and the first equation is true for every n, and therefore it will remain true if we replace these elements in the sum by their averages. And this gives the composition that we wanted. Now this is purely physical space argument. We didn't use any Fourier analysis here, and it allowed us to gain a more general and explicit statement. And having this improved structural theorem, we then wanted to use it and see how it improves the known result, starting with the one-dimensional case. So notice that in this case, in 1D, all these functions are in fact periodic. And this immediately implies that 1 sub A is periodic, namely the set A is periodic. But more than that, the period of these and of the set A does not depend on the chosen tiling A. So as an immediate consequence of our structural theorem, we obtain that for a given finite subset F of integers, all the tiling sets A of Z by F share the same period. And moreover, this universal period has a bound which is polynomial in the diameter of F. And now I want to remind you that from applying the naive pigeonholing argument, we obtain a period on a tiling set A by F, which a priori can depend on the chosen tiling, and the bound on these periods was exponential in the diameter of F. Therefore, this corollary significantly improves their previous one-dimensional result. Now, what does our structural theorem imply in the 2D case? So by applying it to the 2D case, to the proof of Bhattacharyas, we were able to easily deduce that the equidistribution scenarios are in fact impossible. And so any tiling of Z2 must be weakly periodic. We don't need to modify anything. This result allows to reduce the study of the structure of tilings in Z2 to the study of one-dimensional tilings, a question which is still quite open. In fact, our concrete structural theorem allowed us to track the bounds on the periods on each coset of a certain lattice, and we obtained this quantitative version of the previous statement on the weak periodicity of any tiling of Z2. And all this quantitative information is independent of the tiling set A. It depends only on F and the periodic set that we tiled. Now, having this quantitative version, let's go back to the decidability of tilings. The previous method of Bhattacharyas showed only the existence of an algorithm which decides whether a finite subset of Z2 tiles or not. But it didn't give any bound on the running time of the algorithm, namely the computational complexity. In other words, it couldn't answer the question in how much time we would be able to decide whether a finite set is a tile or not. But since our analysis enabled us to track the bounds and the periods relatively closely, we achieved a kind of surprising bound on the computational complexity of the tiling question. And this bound is of exponential type in the diameter of the given finite set F. Another two-dimensional question that we considered, it was actually asked by Michalis Kolonzakis, is the following question. Given a tile F of Z2, does it admit a tiling which is strictly weakly periodic, namely not one periodic? So we already observed that this question is proper because there are tiles of Z2 for which the answer is yes. For example, we saw that this F is one of them, as it admits this non-one periodic tiling. While there are also tiles for which the answer is no. For example, if F is collinear by the one-dimensional result, it cannot admit strictly weakly periodic tilings. Or, for instance, if F is connected in the sense that if we replace any point in F by a unit square centered at this point, any such square will share a one-dimensional face with another square. So we obtain what we call a polyomino. So in this case, it was proved by Gerald, Buchweier, and Nivat in 1989 that such tiles admit only one periodic tiling. That they cannot admit strictly weakly periodic tiling. This result, by the way, was extended to tiles which are topological disks in the plane by Kenyon later in 98. Another example of a type of tiles which admit only one periodic tilings is tiles which have prime order. And this is a consequence of the argument that was presented by Szegedy in 98. Okay, so this is a proper question. And by using our results, we were able to show that this question is also decidable. And we describe an algorithm which, upon an input F, which is a tile of Z2, computes whether it admits a non-periodic tilings or not. In fact, this algorithm computes all the possible tiling sets A for the tile F in finite time. And this is done by using the fact that all these tiling sets are weakly periodic. Now, to conclude, let me mention some questions which remained open. So first, as I mentioned, the main goal of our current project is to study how our new structural theorem can be used to the study of the structure of higher dimensional tilings and the higher dimensional case of the periodic tiling conjecture, starting with the 3D case, which is still open. But also our current approach to the 2D case leaves open questions on tiling of level greater than 1. So first, let me explain what I mean by a level of a tiling. So we say that the translations of F along A tile Z2 at level K, if every point in Z2 gets to be covered by exactly K of these translated copies of F. So when we translate F by A, each point in the space is covered exactly K times. So this is in fact a particular case of a periodic level function when we have only one level. So it will give us the constant function K, but K is not necessarily equal to 1. So in our paper, we show that if K is equal to 0 mod 4, then there are tilings of level K of Z2 which fail to be weakly periodic. But what about tilings of levels greater than 1 that are not in 4Z? Is it possible for such a tiling to be non-weakly periodic? This is still open. And another 2D question which remained open is the periodic tiling conjecture for tilings of higher level in Z2. So suppose that F tile Z2 at level K and K is greater than 1. Could it be that there is no periodic set A such that F tile Z2 by A at level K? So these are some further interesting questions to study. And I'll stop here with this spectacular translational tiling of a share. And I'll thank you.